All right, continuing on with class 21, we just talked about laminar pressure drop, laminar flows, and the relationship between flow and pressure drop, or vice versa. Now we're going to talk about turbulent. All right, so we mentioned these regions of anything below 2,000 Reynolds number. We're laminar. Anything above 4,000 is considered turbulent, and then we do have stuff in between that's transitional. And you can kind of see this chaotic action that's taking place. And it's got sort of even though there's chaos going on, there is a sort of a consistency to the chaos. So we have this idea of it being fully developed. All right, so we can, instead of going first principles like we did for the laminar flow, and those first principles will work out. We'll show here in a second that it's true. What we do is they've created experiments and used the non-dimensional numbers and came up with a repeatable prediction of the pressure drop. And we do that by way of something called the Moody diagram. And I've always thought that sounded kind of funny, right? This thing was kind of moody. And so take a little tour here of the Moody diagram as you're introduced to it. I'll mark it up as we come through. Let's see if we can find one. Where's the little pen thing? There you go. And purple's the best learning color. All right, so first off, we have the Reynolds number here, and you can see that it's a log graph, right? So we got 1,000 and 10,000 and so on. And so you can see right here, we have the lines that are marking this region here of the, and so anything over this direction right here is going to be turbulent. Anything over here in that direction is laminar, and then anything in between is sort of a transition no man's land. This thing appears to be like a straight line right here, and we're going to wonder, well, what is this right here? Well, that turns out to be what we call the friction factor, and we're going to show the equation that it gets used with. It's sort of a combination of a non-dimensional number. I think it was the, 1 second, let me pause. And wouldn't you know it, of course it is. It's actually going to be the Euler number. That's one of the non-dimensional numbers that we have on our equation sheet. It's actually this guy right there is a non-dimensional number. But it's also combined with the diameter divided by the length, or the length divided by the diameter. So the main equation that we're going to use for this in this friction factor, let me see if I'm going to say this the wrong way. I'm going to say this the wrong way, aren't I? This friction factor, you could say is, well, there's also 1/2 in there because we're so used to having Bernoulli look a certain way that we put it in there. Is going to be 2 times the pressure drop divided by rho v squared, but then we would also have the diameter divided by the length, right? So this right here, it is its own non-dimensional number, but you could see that right there compared to that is the Euler number. So you could think of it, and this is called the Darcy friction factor. Darcy friction factor on the Moody diagram. And you could also see that we also have another non-dimensional number right here. And this is going to be the surface roughness divided by the pipe diameter. So we have a whole bunch of different non-dimensional numbers at play together. We have Reynolds number, which everything is sort of dependent on. We also have the roughness ratio of the internal surface divided by the diameter. We also have this right here, which is the Darcy friction factor, which we use to to solve. But we're going to see here in a second what that looks like. Okay. Do I have something else I wanted to say? Yes, I do. Right there. Okay. So I want to write down the equation. that we have, and show kind of do like a little bit of a demonstration as to how this is used, right? So on the previous page for the laminar, or in the previous setup, we had this delta P was going to be equal to 128 mu L, this velocity rate, the volume flow rate, which I wish I had kept as a velocity, but it's okay. We'll get back to it. Pi and d4 right there. So let me write that down, and then just as a quick demo, the delta P is going to be equal to 128 times mu, the length and the volume flow rate, divided by pi and diameter fourthed. Well, what I can do, put this back underneath. I can take, this just is for convenience, I'll take a rho divided by rho, take v divided by v, and 2 divided by 2. This was somebody, a colleague's method of doing this, and I'm mimicking it. I don't know if it's probably an easier way to do this, but it's all right. I'm going to keep using it. 128 mu L v pi over 4d squared, right? So that's what this guy, I could have left him that way before, but I've moved him out. I've taken this v dot and moved it back into a velocity in there. And then divided by, I'm going to take that d and I'm going to separate it out to d, and then pi, and then d squared, right? So there's a number of things that are going to cancel out because of this. But one thing that we can find is we could find Reynolds number. So let's see if I can find Reynolds number. Okay, looking for it. It's going to be this guy and him, and boom, right there. So there's Reynolds number, but upside down, right? Rho v d there, okay? And then other things I'm going to need, we're going to get, these guys are going to cancel out. Boom, pi and pi is going to cancel out. This, I don't know why that 2 and 2 are there, to tell you the truth. That's funny. I don't recall why that 2 and 2 was ever there. It doesn't make any sense to me whatsoever. Forget about him. I don't know what he's doing right there. But we're gonna have rho v squared right there. That's another. That's one of the things we're gonna get out of this. And I think we're gonna cancel those diameters out. That d squared right there. So that helps. And we're going to find this L over D right there. So what you're going to find is, let's see if we can put this together. 128 times our Reynolds number times L over D, and I think I'm going to have another rho v. No, I need to divide this by 2 somewhere, or divide it by. Yeah. So that's what our 2's were for. I'm sorry. One of them is going to divide this and make it into 64. Is that true? Oh, and by the way, I'm sorry. Reynolds number needs to be on the bottom. Oh, I'm doing terrible at this. Darn. So I'm going to practice. All right, so there you go. 64 over RE times L over D, and then rho V squared over 2. Boy, that was harder than it needed to be. So that's what pressure drop is going to be. And let's see, double check that I got everything I wanted out of this. Yeah, here's our L over D, right? Here's our velocity times velocity. So it's velocity squared. There's our extra rho, got over there. This got divided by 2, and that 2 got rid of this and made it to over there, right there. The reason why we want this form right here is that's like Bernoulli's dynamic dynamic pressure, right? And this guy is going to be our friction factor for laminar friction factor, and it's dependent on Reynolds number, as you could see right here. So we have that line right there is describing this. So we have delta P is equal to Darcy friction factor times L over D times rho V squared over 2. And that's where, for at least for low Reynolds numbers, F is going to be 64 divided by Reynolds number. And I'm not sure that I agree that it should be a straight line onto here. We could probably test that out. But anyway, that was the explanation. So I'm going to do my examples in a different video. We'll keep this one short. That's good. Short is better anyway. And I'll probably do 2 examples, but I won't only do one of them in class.